Welcome to Milan. Welcome to the European Microwave Week 2022. I'm Luca Peregrini, the General Chair of this event, and I'm very happy to see that this room is crowded because it means that we have a lot of attendees and probably we are going far beyond our expectation. And this means that we are back to our in-person events. This means that we like to be in touch with other colleagues and friends. This means that the formula of this event is still valid. What we propose is a full week of different events. We have 3 conferences, 3 forums, workshops, inter-society panels, student activities, and also a large exhibition. These are the numbers of the attendees so far, and apart from the details, I'm very happy to say that we have 1,300 unique delegates till now, which is by far exceeding our expectation because we were targeting something around 900. Therefore, this is really well beyond expectation. And in this conference center, right now, there will be roughly 350 people or more as visitor, exhibitor, and conference attendees. We were inspired by Leonardo da Vinci preparing our logo, and you see here, this is the famous drawing of Leonardo, the Vitruvian Man, that want to represent the perfection of the human being. And Milan is the city, has been the city of Leonardo da Vinci for more than 10 years. Leonardo da Vinci is for sure a genius, all over genius, and for sure he was the first real engineer in history. And we decided to use the motto creative microwaves because we need creativity to make a step further for the benefit of humanity. But to stimulate creativity, we need to meet peers, to meet friends, to discuss, to be in touch with other people. We need the human touch. Nothing can replace the human touch. And this is the reason why here we have so many people in these days discussing, meeting, and having good time and also having fun. But to stimulate interactions, of course, you not only need technical session where you discuss with peers about details in our field, but you also need to meet, to make friends, to have good time, to relax, and then to stimulate your creativity, as I said before. And for this, we prepared a full portfolio of social events that span all over the week. We started yesterday, we had 3 concurrent events: the UMIC Get Together, the Automotive Forum Dinner, and a special event for the students. And you have seen probably some pictures coming in this room. Then today we are going to have the welcome reception for all the paying attendees. It will take place on the 2nd floor here in the MICO, in the Gold Room. Then we have tomorrow another bunch of social activities. The Women in Micro, you will have detail, we receive detail later on. And in the evening we have the gala dinner organized in a museum, which is not far from here, but we have buses, transportation prepared, and there are still some tickets if you want to register for this event. And I said before that it is important to make friends, but it's also very important to remember the importance of friends that we had. And this is the reason why we are all indebted to Roberto Sorrentino. Myself, I'm strongly indebted to him. And we decided to organize a get-together of friends that want to come just to talk together here in the exhibition area, just outside this room, tomorrow starting at 4 p.m., close to the booth of the company that has been funded and run by Roberto. And then we have a special event for the TPC members to reward them because they did a great job selecting the technical problem. Maurizio will discuss later on about that. And finally, on Friday, we have the EURAD lunch, which is a typical event we have every year. Actually, this event is back to Milan after 20 years. We were here in the same place roughly 20 years ago in 2002. And I think this is a very well-suited venue for this conference because it is in downtown. And as you can see here, you can reach at a walking distance the castle, the cathedral, the famous La Scala Theater, very fine museum, and therefore it's nice also to have a walk around here in this city. And Milan is a very developing city, very, let's say, modern city, which is developed a lot in the last years. And therefore it's worth a visit also other part of Milan. But you see only one person here on the stage now, but this is of course not the result of a one-man show, but this is the hard work, I would say, of very committed people in my team. You see here their face, and I have to thank all of them, to thank European Micro Association for its support, and to thank also Horizon House for the helpful activities we did together. And please join me to greeting these colleagues, and I ask them to stand if they are in the floor here to receive your applause. Thank you. But now is your turn. I think that a conference or an event like this is nothing without the attendees that make it really a memorable event. Therefore, now is your turn to meet, to chat, to discuss, to interact, and to visit the exhibition, to take part in the social event, because this will make this event a memorable event. Thank you very much for your attention. And now I'm very pleased to invite to the podium the President of the European Micro Association, Dr. Frank van den Bogart, to give his welcome address to the attendees to this conference.
Yes, good morning. That's my name and that's my Yuma outfit, but we're not going to discuss that. First of all, of course, I'd like to welcome everybody here. We are back in Milan. The first Microwave Week that we organized was exactly 20 years ago. That was also here in Milan. We went 2 times to Rome, but we are back in Milan, and I think, Luca, that was a very, very good choice. But I'm not only welcome everybody here in the room, but yeah, Luca did it already, but I think we have a great event. And if you look at your numbers, they're really more than we expected. And that's not only thanks to your team and everybody working in your team. It's also on behalf of Yuma, really thanks to all your team members. And I'd also like to give a welcome to Rashwanda Henderson. She's the president of MTT. As Yuma, we have already since a couple of years an agreement with MTT. We are cooperating together, we are organizing joint events. We are inviting each other to each other's opening session of the IMS and of the Microwave Week. So I'm very, very happy that you're here, Rashwanda. I'm looking forward to what you're going to present later on. And yes, I have to talk about my own car. I was looking forward to this week, and I did see in the program that we are going to visit the Alfa Romeo Museum, and I was really looking forward to that. That was yesterday evening, but there were 2 dinners yesterday evening, and I had to make a very perverse choice, and had to make a choice to go to the other dinner. So I really lost an opportunity to see my favorite cars again. But I went to this dinner, and that was not a bad choice, I think. I think it's anyway very good that we do have those kind of social events in the week. But we awarded Franco Giannini yesterday evening. And Franco Giannini is one of the founders of the Gallium Arsenide Association. And he really deserved that award. But what happened, in fact, I tried to make the picture, and it's not the best picture, I think, but it was very, very crowded. It was very, very lively. Everybody was very enthusiastic. But what we did see over there, we are all professionals. but at the same moment we are friends and we are family. And I think that's one of the most important values of this week. We are friends. Having said that, I'm coming back to one of my slides of my welcome speech in London. We talked there about Ukraine and what happened over there. And I'd like to report a little bit back about what we did as EURMA to support the Ukrainian migrant community. So as EURMA, we really published a firm statement. We did that on our website, we did that on our social media. Together with the EURAP, that's the association behind the UCAP, the European Conference on Tennis and Propagation, we helped the refugees from the Ukraine to find a job in Europe. And together with the MyCon conference, which was 2 weeks ago, we paid together the fee of the Ukrainian delegates at the MyCon, and we also paid, if possible, we reimbursed the travel cost. I'm going to skip this slide. And I also like to pay some attention to our innovation team. EURMA has an innovation team. That's an innovation team of young professionals, and we really ask them to come up with new ideas. How can we improve the week? How can we improve EURMA? How can we improve everything, in fact? We don't steer on that as a board. We give them all the freedom, and we give them also the freedom to carry it out. And they did some marvelous things in the last couple of years. For example, they started with the Internship Award. That's in fact an internship award for PhDs and for master students to do an internship of at least 3 months in a renowned European industry or research institute. We do that now for the 5th time in a row. And the number of applications and the number of host institutes is growing every year. The people who got the award are all very, very enthusiastic. And it's really rewarding. If you do that, it's really, really rewarding. You make friends for the rest of your life, and it's an experience for the rest of your life. So I really encourage everybody who has a PhD or a master's degree to submit an application. The deadline is the 28th of November this year. And really do your best, I would say. It's rewarding. The only disadvantage is that we really ask you, of the winners of the awards, to make a promotion video to tell about your experience of that internship, what you learned, how did you feel about it. They're all published on YouTube, so have a look at that, and then, yeah, if you have that look, then you're convinced, I think, to submit an application. That innovation team also started the webinar series. The first one was on the 14th of June, a couple of weeks ago, a couple of months ago. The next one is just in 2 weeks from now, and we are continuing that. And we are very, very happy with that. And the attendance of that first webinar was very, very good in our opinion. This slide, I'm not going to talk about it. It's about technology. We've showed that several times. It's made by a colleague of the board of mine. And that's what we're doing. We have a full room here of delegates, and I'm not going to insult you, but we might all be nerds or geeks or something like that. And we'll talk about technology, and we love technology. It's not only about technology. And also as EURMA, we published a white paper 2 years ago in 2020. And that was a paper to emphasize the enabling role and strategic importance of wireless technology for our future. But also, if you have a look at this report, you see tables like this one. And that's about money. And that's, of course, very, very important. And you see also that we are developing enabling technologies that push our economy. But if you like to have funding for your R&D, if you like to have attention in Brussels, for example, with the policy makers there and the decision makers, you have to address other issues. So you, in my opinion, you really have to look at the societal, the ethical, and the legal challenges. And I don't think we don't do that enough. And I would really like to see in the coming micro weeks that we also have some efforts in that area, that we have keynotes in those areas, that we have workshops in those areas. And for example, on the climate change, if I browse our program book for the word climate, I see it once. That's an exhibitor who likes to be climate neutral in 2030. But I'm convinced that we are developing technologies that help to cope with those challenges. But we don't say it and we don't promote it. And I think we have to do that more. Exactly with the energy transition. We are doing a lot this week on the energy transitions. We are talking about energy harvesting. We have a workshop on that in that area. We have papers in that area. We had a workshop on a space-based solar energy system with wireless power transmission. So we do a lot of work and developing enabling technologies in that area. But if you are in Brussels and you ask, hey, how does microwave technology contribute to the energy transition? I didn't see any policymaker who gives this answer. And that's a pity, I think. I spoke already about the world before and after the 24th of February. That's when Russia invaded the Ukraine. That's going to have impact on the UMIC, on our UMC, and on the radar conference. Exactly the same as the non-dependency of rare materials. All industries working in this area are talking about that topic, but we don't promote that. And those 4 items are in fact the societal and ethical challenges. The last item, collaborative innovation, that's perhaps a legal challenge. And I'm doing it myself also. If we talk about contracts, we talk about IP, we talk about protecting IP, we talk about hiding IP, but we don't talk about sharing results with each other. And that's perhaps something that we have to learn to do in the future. I call that collaborative innovation. I have seen very good examples of that people are working together and sharing data and sharing results. But we don't see that back in our contracts, and we don't see that back in the contracts, for example, of the European Commission. So the public-private partnership contracts are not really yet at that level. And perhaps you also have to convince Brussels to do some effort in that area. So that gives a couple of examples. If you like to come up with your own ideas like the innovation team is doing, if you have ideas how to promote those societal challenges in the week, think about it, come up with your ideas. I would say try to beat Leonardo. He was very smart, but I think we are smarter. You know where to find me with your ideas. Come to me and we really make it work. Thank you very much.
Okay, thank you, Frank, for this inspiring presentation. And it is my pleasure now to introduce the president of the Microtheory and Technology Society, Professor Ashanda Anderson, that will give us a welcome address to the audience.
Okay, good morning, good afternoon. Thank you so much, Luca. Thank you, Frank. I'm very excited to be here. Just a bit nervous, but that's okay, that's good. But I bring you greetings from the United States and the state of Texas and the IEEE Microwave Theory and Technology Society. And so we're very happy to be here. In fact, our AdCom meeting, Administrative Committee meeting, was held prior to the conference. And so we've had some time to adjust to the time difference, those who are not from this part of the world. And so we're quite familiar with Milano, and so we're really happy to be here. I'm very excited to celebrate with you all the 52nd European Microwave Conference. And I think by the end of my short talk, I'll do some math and share some numbers with you. But just as Luca mentioned, the Vitruvian man, I also believe that his analogy to how man's body and the universe are correlated speaks to how the Smith chart is correlated. So we all use the Smith chart as microwave engineers. So I think that just as Da Vinci was looking beyond, I think what we do in our field is looking beyond what's currently going on. And so many of you in the room are already IEEE members, and so you know a lot about this society, but I just have a couple of slides just as a reminder. It's the world's largest technical professional organization for the advancement of technology. And really the tagline is advancing technology for humanity. And we all have all of that technology, whether it's in our pocket or we're wearing it on our watch, as a watch, but we've seen the advancement in the last 20, 30 years, and it's really the fruit of what goes on in these types of meetings held here at the European Microwave Conference. So we have 39 societies, of which MTT is one, and 7 technical councils. And as I said, I'm sure many of you are multiple members of these, and so you make up the over 400,000 members within the society. And one thing to note is more than 60% of those members now are from outside of the U.S., and we recognize that. And so there are over 343 sections, and we're today in Region 8. And so we want to acknowledge the great work that has been done in Region 8. And another thing as an educator that I find exciting is that more than 25% of the membership in IEEE is made up of students. And so we understand that students are the lifeblood, whether it's the UMA or IEEE MTTS, and we have to engage with our students so that they can have the passion for this field that we have. And so it's so important to talk with them and share with them. So I was very excited to participate in the 3MT yesterday. I pulled this slide from the IEEE webpage, and one of the things I wanted to highlight, which you see in yellow, is that the IEEE partners with more than 1,400 non-IEEE entities globally. And so I liken that to the relationship that Frank spoke about with respect to IEEE MTTS. It's extremely important to partner. There's no point in being isolated in a silo and trying to do it on your own, because it's this global efforts that we put together and build what's great about not only our society, but really our world. So we all know that we reach out to IEEE for IEEE Explorer to obtain publications, and the results of this conference will be published there. And so it's just a really fruitful entity, and I'm glad to represent it, and I'm happy to be here as a representative. And so some just minor things about the society. As of the end of August, we had at least 11,000 members, and 20% of those members approximately are students. So once again, that's extremely important to me. 9% of them are female, and we're continuing to try to grow our female population, because we know the diversity of gender actually does bring about greatness in what we do technically. We have more than 210 active chapters, and they are made up of student branch chapters, joint chapters with other societies, and then full chapters. And so I use this slide to highlight how large Region 8 is and how important it is to the function of not only IEEE, but microwave theory and technology. And on the right side, you see a logo. So we're celebrating 70 years. And so what I wanted to share from a math perspective is 5 plus 2, so 52, 5 plus 2 is 7, and 7 plus 0 is also 7. And so 7 reflects perfection. So I believe that the society, UMA has achieved perfection this 52nd year of this conference, and also we're striving for perfection in our society. And so this is my last slide, and I just want to congratulate Luca, Frank, and the entire UMA organization, and I also want to celebrate what has happened and what will continue to happen over the course of this week. And we look forward to participating next year, and so we will see you in Berlin. So thank you for your attention.
Okay, thank you, Rashanda, and thank you to MTT for the help also provided in the organization. We had several events that are in conjunction, organized in conjunction with MTT Society. Now it is my pleasure to introduce Mariatter, who is the representative of Keysight, who is our platinum sponsor. Please. Marie.
Thank you, Luca, for that very nice welcome. And it's my pleasure to be here again at European Microwave Week. It's an amazing opportunity of 3 forums, 3 conferences, and an incredible trade show. So I hope I get to see you around on the trade show throughout the day. I believe a lot of the conferences have already finished a lot of the sessions. It's wonderful to see you all without masks. It seems like just yesterday, maybe a few months ago, that we were in London, and now we're in beautiful Milan. And I have to admit, Milan is a little bit more of a favorite city of mine than London is. I'm no disrespect to any of the British folks, but it's wonderful to be in the land of Leonardo da Vinci and to really appreciate the curiosity, beauty, artistry, and the learning that we will all embrace this week. There was a book written by Walter Isaacson around Leonardo da Vinci, and it really spoke to me, the saying that if each of us in our own lives became a little more observant, a little more curious about the wonders of nature, and a little more committed to beauty, not only would we have better businesses, we'd have better lives. And I really believe that the sense of curiosity that brings us here enables us to create much more beautiful designs, much more innovation in what we bring to the world. And so I'm very excited about the curiosity that we all bring here, what we will learn, and how we will interact and collaborate together to bring new wonders of innovation. Many of us are involved in so many of these technology trends, and so many of them intersect here at the conference, whether it's in automotive, whether it's in 5G, 6G evolution, even what we're doing with AI and ML, and satellite and sustainability. It's just wonderful to see all these technology trends and the innovations that technology will help bring to the table to make our lives better. And from a Keysight perspective, we're really excited about how we advance innovation across research, across the industry and education. We partner with many universities to advance the communications technologies. We also are constantly looking to how do we bring to the market, first to market solutions, whether it's in communications, whether it's in automotive. And then last but not least, we really play our part, and this was a theme at the last European Microwave, as to how do we advance STEM in education and engineering. And I'm just going to touch a little bit deeper on each of those key areas that we partner with universities in, and how we bring solutions and this STEM effort. The first one is the Keysight research partnerships, whether it's helping support teaching labs, providing contracted studies with universities, or PhD sponsorships. Other examples involve doing deep research with professors, such as what we're doing with the University of Stuttgart, and building out a 320 gigahertz 6G test bed, wideband test bed for them, and really enabling us to take some of the innovations into research further in this new arena. Or alternately, what we're doing with FBH with Dr. Olaf Bengtsson, and it was really expanding what we do with 5G MIMO based on a discussion that happened between Joel Dunsmore, one of our fellows, and the professor, to see what is possible, and it led to the expansion of our PNAX product. And then ultimately, while that was very useful for his research, it really helped us as a company to bring that innovation more to life as we developed it and offered it more in terms of our products. So a very successful and fruitful collaboration between industry and the universities. Another key area of what we do is really investing early in R&D so that we can provide artistry in our semiconductors. A lot of people sit there and say artistry in semiconductors, but it really it is artistry, because measurement science really brings both that science and art together. And what we've done is we've taken our ASICs, if you want, our chips and our measurement science to new levels by investing in gallium arsenide and indium phosphide fabrication, so that we can really take some of those innovations to the limits in terms of what we provide with our measurement instruments, so that we can provide the industry's fastest and most reliable measurements. And then the other topic that's really important to us is how do we advance STEM and engineering education. Right before COVID started, we launched the IoT Innovation Challenge, and it was to really encourage students to come out with new ideas of how to improve the world. This year, we took it in a slightly different direction of how do we create more innovations towards sustainability. And we really wanted to encourage women participation and women-led teams in this. And so I'd encourage you to tune in. We've had lots of submissions. We have 6 finalists, and they'll be all participating for a $30,000 award for the winning team, and also $30,000 of contributions to their universities in electronics equipment. And so this final competition will be live streamed on October 29th, so I hope many of you join in and watch it. But it's a small way, but a good way to raise awareness to carbon neutrality, and also to encourage much more diversity in the participation in engineering. Another key facet that I wanted to touch on is beyond artistry, is beauty, since we're in the city of Leonardo. And a big focus for us at Keysight is how do we bring beauty in our software that ties together all of our instruments with a lot of the analytics and insights. But some of you may look at this and say, well, this looks very much like the CI/CD diagram. We actually want to extend it a little bit further to actually talk about how we take this towards workflow automation. Because at the end of the day, as much as we like to have the best instruments, as much as we look for insights and analytics, what drives many of us is the need for speed and getting to market and innovating. And that's where we take what we do with our software to tie all of those insights and feed them back into the beginning, into the measurement, into the simulation, so that it is truly not just a continuous and virtuous cycle, but one that allows all of you to develop, to innovate, to bring to market many more exciting and innovative solutions. And we bring this across all of those different areas. And it's something that at Keysight we're really focused on. How do we make software much more of our DNA to tie together the different measurements across the different solutions to allow us to better model whatever problem you're trying to simulate, whatever problem you're trying to emulate, and help give you the best insights so that you can keep developing the latest and greatest innovations for all of us. And so I know many of the conferences went on earlier yesterday and earlier, so I hope many of you got a chance to participate and enjoyed some of our Keysight speakers. I'd like to welcome you to come by our booth and have a coffee with us and talk to more of those speakers. They'll be around our booth today. And I want to wish you a wonderful conference, and thank you for the opportunity to see you again.
Okay, thank you, Marie, for sharing with us your thoughts and also especially the initial part that I liked very much. And now it's my pleasure to invite my colleague and friends, Maurizio Bozzi, who is the General TPC Chair, to give you a briefing of the technical activities that are within this week. Please, Maurizio.
Good morning, ladies and gentlemen, and welcome to Milan, welcome to European Medical Week 2022. In this short presentation, I will illustrate the schedule of the UMW 2022, and we have to say that the program of the week follows the traditional schedule, so we have the three major events, the three conferences, the UMIC on beginning of the week, Monday and Tuesday, UMC from Tuesday to Thursday, and then URAD from Wednesday to Friday. And besides the major conferences, we have a number of workshops and short courses, more than 30, that are beginning and end of the week. So we had Sunday, Monday, and we will have Friday. And then we have three quite well-attended forums. We had the Automotive Forum yesterday, and we will have the DSS Forum and 5G, 6G Forum in the next few days. We also have a quite intense program for students. We had two doctoral schools, actually the second is still running today. We had yesterday the Young Professional event in conjunction with MTT Society, and we had the 3-minute thesis. And of course, we have a quite big exhibition. You have seen just outside of this room that we have a quite packed room with a lot of exhibitors, and the exhibition will start today and will continue until Thursday evening. Moving to the paper submitted to the conferences, here you see some numbers. Overall, we had around 600 papers submitted to the conference. The number is not that high, but you know, this year we had two conferences, the UMW 2021 that took actually place in March, so it compressed a bit the space for UMW 2022, but still we had a quite good number of papers and a high quality. And they were divided 60% UMC, 20% UMIC and URAD, more or less. And the Technical Program Committee selected more or less 2/3 of these papers, approximately 400 papers that were accepted between oral presentations and posters. And the Technical Program Committee was able to generate out of these papers 75 regular sessions. And the novelty of this year is that each technical session starts with a keynote speech, either academic or industrial keynote. And the idea was to bring well-known speakers with a broader scope in their presentations, like tutorial and overview papers that can be interesting, especially for young professionals. Besides the regular session, we have 5 special sessions, the traditional one in conjunction with the APMC, and then we have one organized together with EURAP, the European Antennas and Propagation Society, and 2 geographical special sessions, one related to the micro-research in North Africa and the other for micro-research in India. And we have a memorial session devoted to our friend, Professor Vittorio Rizzoli. Besides that, we have 7 focus sessions, 2 panel sessions that were organized together in conjunction with MTTS that will take place tomorrow, one devoted to biomedical applications and one devoted to materials that I hope will be very well attended and interesting. We have 6 opening and closing sessions, 2 per each conference, and 5 poster sessions. And overall, we have the round number of 100 sessions that I think you will enjoy and represent a quite intense technical program. Of course, the technical program is not generated by itself, but it required the work of a number of people, and I would like to thank them very much. First of all, the chairs of the 3 conferences, Marco Pasian for Technical Program Chair of UMC, and then Alessandro Cidronali and Rocco Gioffre for the UMIC part, and Deborah Pastina and Fabiola Colone for URAD part. I want to have a special word, a special thank for these 3 people, for Mark, Christine, and Matthias, who helped a lot with paper management software. So their help was really precious, and I wish to thank them. I also want to thank the TPC members, the Technical Program Committee members. You see here all the names divided for the 3 conferences, and they did a very good job. It was online this year. There will be an event devoted to them, to thank them. On Thursday there will be a TPC luncheon, and they are all invited to attend. And I also wish to thank the reviewers and the authors who submitted the paper. So this concludes my short presentation. I wish you to enjoy the European Micro Week, enjoy the city of Milan, maybe not too much during the technical sessions, but have a great week. Thank you.
Thank you, Maurizio. As promised, I brought the sun for you, but stay with us in the conference center. Then, now it is my great pleasure to introduce the chair of the European Microwave Conference. My colleague and friend Alessandra Costanzo will give you some remarks about the conference and then run the remaining part of the session.
Good morning, everybody. It is a great pleasure to be here with you. I am Alessandra Costanzo, the chair of this European Microwave Conference, and I would like to also acknowledge my co-chair, Dr. Luca D'Antoni, please stand up, and the TPC chair, Professor Marco Pasian. We worked very well all together, and we hope we have prepared a very nice program. Welcome to Milano. As my colleague said, it is a mix of a very wide kind of cultures. I really like also to highlight modern arts, such as the vertical hood that I invite you to see, and all other stuff that we will see if you go around to Milano. As we have already seen, we have a lot of interesting sessions, stimulating sessions and focused one. I am very happy to have 3 plenary speakers, workshop and short courses. And also, as usual, we have a session, a technical session, where we have invited women scientists, and in this case, given the site, we thought of wearable devices and how our women colleagues are able to come from engineering to meet creativity. As already said, many of you have already attended the schools. The 3-minute thesis was a very successful event and was really enjoying a lot of people. And also we have a lot of young professional activities that we encourage you to follow, and we continue the tradition to have a career platform where attendees can meet industries and companies related to the microwave fields. In particular, as you know, tomorrow afternoon, part of the afternoon will be dedicated to the women in microwaves. We will move from here to the Pinacoteca Ambrosiana, where the technical session is first held there, and then we will have a visit to Pinacoteca Ambrosiana. I want to take this opportunity to announce that we have organized a bus transportation, and registered people will be reached by email for the details of the transportation. This event is full booked, almost, I think, now, and we are very pleased. I would like to thank Professor Giuseppina Monti, who was the chair of this session. And we are very happy to have with us three outstanding plenary speakers, Dr. Dana Henderson, just after my talk, and Professor Andrea Massa and Dr. Frederick Gianisello during the closing section during Thursday afternoon. It is now, and also we will have some ceremonies, awards, the one just after the plenary speaker, that are Yuma Pioneer Awards, Distinguished Leadership Awards, Roberto Sorrentino Prize, and recognition for general chairs, and also the International Journal of Microwave and Wireless Technology Best Paper. And during the closing session, we will have the Best Paper Awards sponsored by JMA Wireless and the Student Papers finalists. It is now my great pleasure to introduce you our plenary speaker, Professor Dana Henderson. He will give us a talk on a significant emerging technology in our community that is entitled Quantum Technology, Where Maxwell Meets Schrödinger. Dr. Dana Henderson is founder and chief strategy officer of CoQuanta, Inc., and is a professor of physics and electrical engineering and a fellow of the JILA Institute at the University of Colorado Boulder. He received a BSc degree from Cornell University and his PhD in quantum optics from the University of Arizona. His thesis focused on the new technology of ring laser gyroscopes. Dr. Henderson has published over 100 scientific papers and is a fellow of the American Physical Society and of Optica. He is a recipient of numerous awards, including Optica's Wood Prize for his work on optical neural networks and the Lamb Prize for his work on atomtronics. I am very pleased to introduce you, Professor Dana Henderson.
Well, good afternoon. It's an honor to be speaking with what I view as one of the most innovative and practical communities I know of. So it's a pleasure to be here, and I hope I'm able to tell you something that you didn't know before, although I suspect a lot of you know quite a bit about the general topic. So let me get first to what is humankind's most quantum thing. And humankind's most quantum thing is a timekeeper, that is a clock. So here are a couple of recent papers published in about 2019. And don't worry about the papers so much, and don't even worry about this graph too much if it's not familiar to you. This is a plot of something called the Allen deviation versus integration time. And shown here on the top right are various curves for the performance of various clocks. The one on the top right, labeled CS for cesium, is what keeps today's time in the world. Here in Italy, in France, in the US, all use a common clock technology, an atomic quantum clock called the cesium clock. Today, quantum has improved timekeeping technology by a factor of 1 million. And getting a factor of 1 million anywhere is very rare. And this is what I want to calibrate you to what quantum potentially has to bring to an increasing variety of fields. So down is good, and today's high-performance clock that's sitting in a lab somewhere, in fact, sitting in a lab in Boulder, Colorado, where I live, is 1 million times better than the timekeepers that keep world time. And in fact, another way of looking at it is these clocks measure something to better than a part in 10 to the 20th. That's incredible precision. So let me make my way towards that kind of technology by giving you a few aspects of quantum technology. As I say, some of you are probably familiar, some maybe less so. But for most of us, we're used to thinking in terms, for example, of bits. And here we have a bit. I have a 5-volt voltage source, switch is closed, 0 volts across the terminals, and we call that 0. Switch is open, voltage across the terminals is 5 volts, we'll call that a 1. We're very used to that technology being the foundation for our computers. In the case of quantum, the physical value of a qubit is given by a vibration. So think of a violin string or piano string oscillating in its fundamental. The lower frequency, the qubit has value of 0, rather arbitrarily defined, but conventionally defined. And say the harmonic of the vibrating string would be called a 1. Simple enough, but the point is, clearly, you can think of a combination of vibration, a 0 and a 1, to give a more complicated vibration perhaps, a little prettier tone if we're thinking about music. But the point is, superposition of two states is allowed in quantum. It's not allowed so much in classical. What's the superposition of 0 and 1? Doesn't really make sense. It's certainly not 2.5. So qubits can be a 0 and a 1 simultaneously. And the value and the merit of that I will get to rather later in the talk. Now, what are the rules of quantum? The rules are this. First, a single system can never be off. It is always vibrating. The vibration is never not there. It is never 0 vibration. So wait forever, a system will still be vibrating, and the state of lowest vibration is called the ground state, and it will live forever. Vibration is quantized. It cannot be made louder or softer. So there's a vibration, a 1. You could say, well, can I amplify that? The answer is no. That's not how quantum works. If you want something louder, you need more of those vibrating strings. And then finally, two systems in the same state can get out of sync. This is something this community is very familiar with. We call it in quantum decoherence. So if you start out with 2 vibrating strings and you wait a while, they have finite Q, right? So eventually they got out of sync. They can still be vibrating according to the rules of quantum mechanics, but whereas they started in phase on the left, they're out of phase on the right. So that's decoherence, and that's a big deal in consideration of quantum systems. And finally, what I call the essence of quantum, and this is you've heard of, I'm sure, but just to build it up, the story up for later, we can have a qubit, as we call it, for example, in a superposition state of 0 and 1, and it's written in Dirac notation this way on the left. It's in a linear superposition. But now if I make a measurement of that state, I'm going to get only one answer. That system is either in a 0 or a 1, 50% chance. I can't predict which state I'll get. And the remarkable thing about quantum is you can prepare a superposition state, but you cannot measure a superposition state. So this is like putting RF through a polarizer. It's going to come out aligned with the polarizer, or it's going to not come out, in which case you conclude it was perpendicular polarizer, but you can't determine really what the input polarization was. And that's a peculiarity and a property of quantum that plays a very important role. And the measurement of the induced change, I started in a superposition state, ended up in a single state, that's called collapse of the wave function. Some people call that a lot of mystery. I do not. It's perfectly predictable and understandable, but it is a characteristic that the wave function collapses into one answer or the other. And the inability to precisely predict is called the Heisenberg uncertainty principle, or manifestation. All right, so those are some of the rules of the game of quantum. Now I want to talk about quantum technology. There are a variety of quantum technologies out there. Many of you will be familiar with superconducting quantum technology. My brand is working with atoms. And that's because atoms, for a lot of reasons actually, but atoms are extraordinarily, for example, color selective. So here I have a blue atom. All my atoms are blue today. And I can shine light onto this atom But if I shine the wrong color, quotes around wrong, nothing happens. On the other hand, if I shine on a resonant frequency of the atom, it responds very strongly by absorbing and subsequently re-emitting that light from the atoms. And atoms are, in fact, very, very picky about what color of light they like, and that's what makes them valuable. So atoms have incredible frequency selectivity. Rubidium, for example, is an atom we use frequently because it's an easy metal to work with. It looks a lot like hydrogen in many ways, except you can shine laser diode light on it, like what would come out of this laser pointer if I turned it on. There it is. There's a red dot. I'm red colorblind, so I don't see it, but many of you do. So it takes almost that color. So it's a silicon of sensors in some ways. And so if I take rubidium-87, here's the frequency to which it's sensitive to. Count the number of significant figures, 1, 2, 3, 4, 5, 6, 7. And I've illuminated the 8th and 9th because if I shine light and change the frequency of that light by the last 2 significant figures, I can tune in to resonance and then out of resonance. I think there's a little delay for some reason. So if I tune it just right, you see the last 2 digits change, I get a strong resonance. Let's look at strontium. The clock I told you about used strontium. It's incredibly frequency selective, and it's used in the world's most accurate clocks. Here's the frequency to which it's sensitive to. Count the number of significant figures, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 and 18 significant figures is how sensitive it is to the frequency of the laser light you shine onto it. This is 10 to the 14th hertz. That's in the blue, anyway, it's in the blue. The upper one is in the red. This is about the blue, or a little redder than blue. You shine light on it, and it becomes very, very sensitive to the frequency. So effectively, atoms have extraordinary Qs, right? Unbelievable Qs, and this community knows the significance of having something that's high Q. So now I want to go into one application of quantum based on atoms. And that application is the antenna of the atomic world, the antenna we use to do RF detection. And it's called a Rydberg atom. And a Rydberg atom is any atomic species in which you excite an electron to a very high lying level. So here's an atom. We're going to excite one of those electrons using light so that one of the electrons is going about the nucleus and the rest of the charges very far away. That becomes a very sensitive system. Its dipole moment is very large because it goes, the radius of the orbit goes as the square of the principal quantum number, meaning the higher the principal quantum number, the higher the dipole moment, the more sensitive it can be to electric fields. So we can use this to detect electric fields very sensitively from covering megahertz to terahertz and above. And so let me explain a little bit about that. So atoms, as you know, have discrete levels, and the levels get closer and closer together the higher and higher energy you apply to the electrons. So a first step might be optical, and then another optical step will give you a set of levels, so I've expanded them here. And as you excite the electron in an atom, the levels become closer and closer together. So in fact, you can always find a pair of levels separated by a frequency of interest. All right, so I can find a pair of levels that are separated anywhere from megahertz to terahertz, and then this atom becomes resonantly sensitive to that particular RF or microwave frequency. All right? And we can read that out by something called electromagnetically induced transparency. It's a fundamentally quantum phenomena. It's actually very remarkable. What's also remarkable is it wasn't discovered until the 1990s, which is pretty late in the world of quantum. So here I have 2 levels, 0 and 1. And I shine a probe beam to excite the atoms into level 1. In principle, if I have a cell with this atomic rubidium vapor, say, and I send this probe beam in, notice it doesn't come out, and that's because it's absorbed. So I have a detector out here that detects nothing. Now I consider another high-lying level, number 2, and if I shine on this coupling laser, something rather remarkable and surprising happens. Shine in this coupling laser beam, and it turns out that it can induce transparency for the probe beam. And that's a quantum interference effect. I won't go into it for the moment, just keep it in mind. I have the coupling beam there, and I can turn off the absorption of this probe beam. So when this coupling beam, shown in blue here, is present, the probe beam is detected at the detector. All right? And again, that remarkable phenomenon, electromagnetically induced transparency, is a quantum interference effect. So now I can use this to detect radio frequency signals. So here's that same concept, 2 levels, probe, coupling beam. Here's the atomic vapor cell, probe going through. Because the coupling beam is present, the optical detector sees the probe beam. Now I consider a 4th level, not to scale, such that the difference between the energy levels 2 and 3 is resonant for some RF frequency of interest. Well, when that RF signal is present, it destroys the ability of the coupling beam to suppress the absorption of the probe beam. Sounds like a lot of words there, but let's just say when the RF is present, now the probe beam isn't seen by the detector anymore because the presence of the RF destroys the electromagnetically induced transparency process. So RF is present, probe goes away, take the RF away, the probe is present. All right? So that's the idea. And you can make an extraordinarily sensitive system this way, but what's also unusual is that I can consider shining a different coupling beam there. So now I'm going to take another pair of levels that I show as 3' and 3, and 2', for example. So 2' and 3', excuse me. And now a different color coupling beam allows me to be sensitive to a different RF frequency. And it's the same probe beam that is detected, its absence or presence. So the system that's detecting the RF doesn't change. The probe and the detector, only the color of the coupling beam changes to tune the system to a different RF frequency. So there are a lot of things that this brings as new capability, but before I get into those, let me just say what the state of the art is, at least in our lab. These systems are fundamentally sensitive not to power, as you may be used to, but electric field. And the state of the art is about 18 nanovolts per centimeter per root hertz at about 11.37 gigahertz, all a little bit arbitrary frequencies here. They were just convenient. But it scales you to bring this down home to something more familiar. So this is just some data to show that it's real. This corresponds in this case to about minus 54 dBm power sensitivity in the system. I don't expect you to remember that. I just felt this community wants to see data plotted somehow, and this is, as I say, state-of-the-art performance. But what's it good for? So here's the system, and the sensitivity can be from megahertz to terahertz simply by changing the color of the coupling laser. It's sensitive directly to electric field, not power. Its projected sensitivity can be on the order of 1 to 10 nanovolts per centimeter. The bandwidth can be extremely narrow, a kilohertz, independent of the RF frequency carrier frequency. So even at 100 gigahertz, the bandwidth can be a kilohertz. That's a little unusual. And you can think of doing things like carrier aggregation, detecting many RF signals, all with a single probe laser. So furthermore, the detection volume is about, I've got my fingers separated by about an inch, and it can be smaller, about the size of a sugar cube. So the point is, this is a different technology And folks developing this technology, like myself, don't really know much about the systems that are deployed in the real world. So for especially the younger folks who are looking for something to do, here's a call to all RF systems engineers to take maximum advantage of a wholly new set of RF capabilities. And that new set of capabilities will require innovation based on the expertise of RF engineers, RF receiver system designers, and atomic, molecular, and optical physicists. Sometimes, we'll just call it a lot of words, but folks that are trained in quantum optics and matter. And there's currently no corresponding transmitter technology that would go along with this. So this is just for detection these days, although that can change. So here's some new technology that's on the forefront of where quantum sits, looking for very good applications, offering new capabilities that are very unusual in this RF domain. All right, that's a chapter. We're going to switch chapters. So quantum is much ado about signal to noise. And although that's not often the story we tell, that's the case. And so we look to move from thermal to quantum behavior. Many of you are certainly familiar with systems that are limited by the thermal properties. For example, the Johnson noise associated with a resistor, which is dependent upon the temperature. All right, the power, noise power is proportional to temperature. All right? In the quantum regime, we operate at temperatures near absolute zero. So at absolute zero, thermal noise vanishes, quantum noise remains. You're familiar with quantum noise, perhaps, for example, photon shot noise. And so we say a system is quantum when quantum noise dominates over thermal noise, which doesn't necessarily tell you you're operating near zero. It just says you're operating at a temperature that's low enough where you can ignore thermal noise and quantum noise simply remains. And the quantum limit, when I refer to it, refers to the ultimate performance dictated by quantum noise given a finite set of resources. We'll return to that story in a moment. And I want to tell you about something which is routine in our world, but it may not be very familiar to you. And that's using lasers, completely counterintuitive, using lasers to cool atoms to exceedingly low temperatures, in fact, near very close to absolute zero. And we start here with an atom. This time it looks like a green atom. If I shine on resonant laser field, well, light carries momentum, says Maxwell, and that will give this atom a kick. So instead of using it to give atoms a kick, I'm going to tune, there's a lot of kicks right there, so we can accelerate atoms with laser light too. But now I'm going to tune a laser below the resonant frequency of the atom. And now, if I put an atom in this laser beam that's moving, the atom witnesses a Doppler effect of the laser light. So this technique is used to cool atoms, I'll show you in a moment, and was the basis of the 1997 Nobel Prize in Physics. And here we go. We have two laser beams, one from each direction, the left and the right. And I place an atom, and suppose it's moving towards the left-hand beam. It sees that beam Doppler shifted up in frequency, which is closer to its resonance, and therefore it absorbs that light. The light carries momentum, the atom slows down, and slowing down is cooling. If the atom is instead moving towards the right, it instead is tuned towards the laser beam coming from the right, and now absorbs that energy, and again, it slows down that atom. And this way, I can get atoms cold, because cold means not moving. All right, so what's remarkable, especially, is that if I take a reasonably powerful but not incredibly powerful laser diode, say 10 milliwatts or 100 milliwatt laser light, and shine on rubidium atoms, I can apply a cooling force that's equal to about 1,000 Gs. That's a very large force. 1 G is the force you feel due to gravity. 1,000 Gs is a whopping force. So we're using laser light to cool and hold these atoms in place like bricks and mortar. So although it seems very floating around, it is not. It's huge forces we're applying to these atoms, and we can cool them down very close to absolute zero, very efficiently in a very small system. That system is called the magneto-optic trap. And then back home where I live, I had two colleagues, Eric Cornell and Carl Wyman. Add to that Wolfgang Ketterle from MIT, who said, well, if you get atoms cold enough, and if you get them close enough together, there's a whole other form of matter that forms, and it's called the Bose-Einstein condensate. And this is a very famous set of pictures on the lower right here. The numbers are in nanokelvin, 10 to the minus 9 Kelvin, 400 nanokelvin, 200 nanokelvin, 50 nanokelvin. And what you're seeing is literally a snapshot, false color image of a cloud of atoms. And as you see the temperature goes down, you see the spire sticking out. And this spire is a quantum state. All the atoms collapse into a single wave function called the Bose condensate. And this is what won these three the Nobel Prize. And from my point of view, this was a new technology in the making. This is as significant as the first laser. It is for atoms what laser is to light. And I, being a practical physicist, thought, okay, this is going to be important someday. It took a little longer, but indeed, it's become quite important both in physics and in technology. And this BEC is just one form of ultra-cold matter. There are Fermi gases, there are atoms in optical lattices. Quantum computers are a form of ultra-cold matter when they're made of atoms. And in my world, we changed the technology. So this is one of the original BEC systems. It took about the size of this platform here and quite a bit of room. Put it in a machine, and then twice it's been launched on a rocket. It's been operating on the International Space Station for 4 years now, every day. So this is not still laboratory technology. This is deployed, still early, but deployed technology that can be launched on a rocket. Here's Eric Cornell. I had the honor of watching the launch with him. And this is Christina Koch putting the second generation system on the International Space Station. It's about the size of a dorm room refrigerator. So just to, can't help, all of us can't help but kind of like the technology that we've been working with so long, to just give you a perspective. One of these systems, when you see it in the lab, the atoms sit in a glass cell that's about 2 centimeters wide, so about that wide, if you can see my fingers. It has something we call an atom chip at its very surface. The cell itself is at room temperature. This glass is at room temperature, the chip is at room temperature. When we form a condensate, it's only about 200 microns from the atom chip, from a room temperature chip, and it's at 100 nanokelvin. It's just rather remarkable to understand how good vacuum is at providing thermal insulation, and it's remarkable that you can have this quantum state of matter, something you can look at with a microscope through the chip. So that's where some of the technology sits, has tremendous potential in RF receiving, in inertial sensing, in clocks, and other things. And just to, again, scale you to this kind of system. So when I have this BEC, here's it reversed at 50 nanokelvin to a 500 K. If you couple these atoms to a microwave field, say 10 gigahertz, if you couple efficiently, one photon from 10 gigahertz, from a 10 gigahertz source is enough to entirely melt this quantum matter from the 50 nanokelvin that we used to create it all the way back up to about 500 nanokelvin. So the sensing potential, we're not ready for this, but the sensing potential of this ultra-cold matter is considerable. All right, that was chapter 3. Let me go into the next chapter, which is entanglement. And entanglement is about changing the measurement game. You've probably heard of entanglement. It's often said with kind of a mystical, entanglement, quantum magic. I'm going to bring it back home for you, because entanglement, in fact, is very much a classical notion. Suppose I want to make a measurement of frequency f of an oscillator. In this case, I have a harmonic oscillator, and I want to measure the frequency of that ball oscillating back and forth. Well, I can do it, and I get an uncertainty in my measurement, delta F, from a single measurement of the oscillation frequency. Maybe I'll count the oscillations over a minute, for example, and get an error. If I want to improve my measurement, I might make copies of that system and make lots of measurements. All right? Now, it's not a precise frequency, so I make lots of measurements. How does that uncertainty scale with the number of oscillators? Didn't think I'd ask you a quiz, right? It scales as root the number of oscillators. So the uncertainty scales as the original uncertainty divided by root n. So I can instead entangle these systems by coupling them. And I can couple them by allowing the plate on which they set to move on some bearings. And so now, when they start oscillating, they'll oscillate together. And since they're no longer independent, my uncertainty doesn't scale as the square root of n, but it scales as n. And in principle, considerably better measurement scaling with the number of systems by a factor of the square root of n. Now, in principle, this plate should be oscillating with the atoms, but I couldn't do that in Microsoft PowerPoint. So I gave up on that. All right, so the plate would be moving a little bit. And that's entanglement. And that's how it can be used to improve measurements. Now, the meaning of quantum entanglement, I need to combine with something else that involves measurement. So let me have another example. And here are my two original qubits, one in the ground state and one in the excited state. Now, this is quantum magic. I mean, this is, for me, the focus of the mystery of quantum mechanics. And I don't think quantum mechanics is all that mysterious. It's just that when you keep asking why, you can't answer the question of why this is true, but it's true. So here's a vibrational string in the ground state, one in the excited state. I'm going to entangle them. And if I entangle them right, I can create two systems. So think of coupled oscillators, coupled pendula. I can create two systems which are each in a linear superposition of 0 and 1. That's what I have here, just different phases of the linear superposition of 0 and 1. So I write this the following way. On the left, I have two qubits that I know what state they're in, so I write them in Dirac notation as a 0 and a 1 right next to it. But when they're entangled, I've got two qubits, each of which is in a superposition state, and I don't know which is which. So I have 0, 1 plus 1, 0, where the first number is the lower one, say, the second number is the upper one, and I don't know which states they're really in. So here's why people are investing so much into quantum computing and quantum communication. Because there's tremendous value in this characteristic. So here are my two superposition states, entangled. Entangled is the key word here. Quantum systems. I write it that way, and now I think about making a measurement. And in the measurement on the right, the upper one is going to be a 0, 1. The lower one is going to be 0, 1, and I can't predict it. But let's say I make a measurement of this one, and that vibrating thing is going to be here in Milan. And I'm going to take this one home with me to the US in Boulder, Colorado. And here in Milan, you're going to measure the upper one. And let's say, for example, that you happen to find it in the 1 state, in the upper. The remarkable thing is then you know when I make a measurement back in Boulder, and we haven't talked, that I'm going to measure a 0. All right, guaranteed. And that's a remarkable aspect of quantum mechanics. It's consistent with energy conservation because I started with 1 quantum in the upper state, and I ended with 1 quantum in the upper state. But in the measurements, how did you know that I in Boulder am going to measure the ground state? You know it because you measured the upper state. And that's the value of quantum, and it's used in a lot of things. The fact that the measurement of 1 qubit determines the state of the other qubit, and you can in fact do this with lots of entangled qubits. And one of the things that's used is in quantum computing. So I'm going to give you a made-up problem here and try to say what the advantage of quantum computing is supposed to be. So suppose I gave you the homework problem that you have this number m is n cubed plus n to the 5th plus n to the 7th plus n to the 9th plus n to the 11th modulo 16. Remember, modulo is clock arithmetic. It says the largest number you can get is 15. When you get a larger number than 15, you subtract 16, and then you get the new remainder. All right, so that's the goal. Find the integer. Well, I did this, and I did it brute force by programming Excel. And I start with the integer 0. I program my Excel to calculate this value. And you stick in the individual numbers. You see what comes out. And then finally, one at a time, and you keep track of each output. So 3 gives you 7, et cetera, and you try them all, and after you've done all 15 numbers, which you don't actually have to do, but that's the easiest thing to do in Excel, you know which one gave the maximum. M equals 15 for n equals 11, and unless you're a number theorist, you wouldn't have known that except by brute force. Now do it with quantum computing, entanglement plus superposition. What you can do is you can superimpose all 16 numbers at once. And you can ask it, what's the maximum? And it will just give you the answer in one fell swoop. So superposition entanglement brings speed, vastly faster than parallel computational as well. And so consider this. If, for example, it took 1 second for me to calculate this, which is very slow, but it doesn't matter, then that was with 4 bits, 16, 0s, 15. 5-bit numbers would take 2 seconds. 6-bit numbers would take 4 seconds. 7-bit numbers would take 8 seconds to solve that particular problem. And 29-bit numbers would take a year. 63-bit numbers would take a time average in the lifetime of the universe. And even if you speed the computation to be a microsecond or a nanosecond, you quickly realize that you can't solve problems like this. So a large class of problems are numerically hard, and for all practical purposes, when they take longer than the lifetime of the universe, they're impractical. So the hope of quantum computing is that you can solve problems in finite time you couldn't solve before. Just to show you a picture, there are a few of us in the world that, including in France, there's a group, and one now in Germany, and a couple in the US, that try to do computation with atoms. And here's a picture of 1,225 atoms array. First of all, this is remarkable because this is a picture of individual atoms, actually a snapshot. And the goal is to try to control the wave function of these atoms. And to give you a reason why it's going to take us a while before we have a good computer, it's because controlling these atoms means controlling a wave function which has over 2 to the 1,225 degrees of freedom. And that's hard. And that's why noise is so important to control. All right. So the common of quantum, it's atoms. For us, it's atoms in RF, even in that was IBM quantum computer, I believe, or Google's, but I think that was IBM's. Needs lots of RF. You've heard of quantum often thinking in terms of quantum computing, but there's a huge range of applications of quantum. As you saw, RF detection, clocks, inertial sensing. So computing, if you've heard of that, is just the tip of the iceberg. Most of quantum is below the line of the water that you might have seen so far, but that's where its power is. And my favorite topic in quantum involves atomtronics, the analog of electronics, but using atoms in their quantum state. And we too also need Smith charts, et cetera, to understand how they behave. So here was a more than 1 million factor of advance in the clock. I just want to say quantum is here to stay. The laws of physics dictate the limits of how well any task can be done. And modern technology has brought us to a point in which quantum limit is accessible to an increasingly broad range of quantum applications. And in the future, if you're not operating at the quantum limit, you will not be competitive. And that's why there's so much interest in quantum technology as it's bringing about a revolution. It may take some time, but it's coming. Thank you very much.
have time for questions to this very interesting overview and presentation of quantum technologies. If you can use microphone. Came to my mind first one questions concerning the relationship with our microwave community. Can you comment on how is the complexity of your receiver approach with respect to our RF approach for the detection of the signals?
Well, let me first say a few things. One is there's an enormous demand, first I'll say, for RF engineers in quantum computing, whether it's RF-based, whether it's superconducting-based or atom-based or what, because it involves control of high-frequency pulses, for example, with extreme precision. And then in terms of RF detection using atoms, it has enormous potential. In my view, as a practical application, it is not yet validated. It's not validated until a member of this community actually decides they want to use it. And that there's a booth out there with a company that's selling RF detectors for, to the community. But as I said, it has this enormous potential, and there's a gap between those of us who are developing that potential and those who are potential users of that new capability. And it will take some collaborative work to understand how to best suit this new capability to perhaps even a new kind of infrastructure in RF systems. There's interest in using them in base stations and using them in very low frequencies to replace long antennas with very short systems. There's interest in using them for covert communications. All of these are reasonable potential, yet to be realized.
Thank you very much. There are other questions or comments? So
Thank you very much for the very interesting presentation. And if I correctly understood, the fact that you have the superposition of states allows you to process some algorithms very fast. Okay, in principle, I can understand this, but I cannot understand the process in which you take this information practically. How can you recover the results from the fact that there are superposition of status? I don't know if it is clear.
So the burden of quantum computing really rests with good algorithms. But in the end, if you've done your algorithm right, it's the same as effectively, it's too simplified, measuring the output polarization. In other words, your computation doesn't end up with a superposition. It ends up with a very well-defined state, but in the middle, you've made very, very good use of that superposition space to handle data and so on. So in the end, your polarizer, is vertical, the thing comes out or it doesn't, that's your answer. But it's really key to get the algorithm such that that indeed gives you what you're looking for, taking advantage of the superposition before you get there.
How you can select your answer in this process?
I'm not sure if this will answer your question fairly, but this is the best I can do for the moment. Every algorithm, every process boils down to logical gates, just as they do in conventional computing, right? But these logical gates are quantum. So every algorithm ultimately boils down to understanding how to manipulate logic things, typically either one qubit or a pair of qubits with entanglement, and then building up entanglement, sort of pairs at a time. But it all boils down to very, very simple basic operations. The measurement, likewise, ends up being conceptually quite simple, equivalent to measuring the polarization state. And it's the algorithms which are really where all the magic and remarkable things happen to take advantage of this. The biggest algorithm I can point to that everybody loves to say, here's why we're doing quantum, is called Shor's algorithm. It's the algorithm for decoding, finding the prime factorization, so two prime numbers that make up a very large number used for encryption. And it takes quite a while to understand, finally, how that algorithm actually takes place in the quantum computer. But it's the example to follow if you really want to spend some time understanding it. Okay?
Okay, thank you very much.
You're welcome.
Thank you very much again. Thank you again.
Thank you, Alessandro.
And we have a present for you.
Ah, thank you. Excellent. So I'm delighted. Thank you. Thank you again, Alessandro.
Now, there is the moment for the European Microwave Week 2022 awards ceremony. So I give the podium to Dr. Andy Gibson, Chair of Awards Committee.
Thank you, Alessandra. That was a fascinating talk there from Dana. I'm just glad that I'm not now doing a technical presentation. So I'm Andy Gibson. I'm chair of the awards committee. I'd just like to thank some of my colleagues who helped me with this. Gilles Dombrine, Holger Meinl, Josef Medelski, Noriharu Sumatsu, and Andrew Wilson, who also helped. Just to start off by thanking my colleagues. So UMA is proud to acknowledge individuals who've made exceptional contributions to the microwave community. And these awards have been going on since 2004 with the introduction of a Distinguished Service Award. But altogether, there are 5 UMA awards: the Outstanding Career Award, the Distinguished Service Award, Leadership Award, a Pioneer Award, and Roberto Sorrentino Prize. All of these awards consist of a bronze medal carrying the name of the award and the name of the recipient. This event, 2022, we're giving 3 awards to be presented: the Pioneer Award, the Distinguished Leadership Award, and the Roberto Sorrentino Prize. So without further ado, the Distinguished Leadership Award is a new award to be given for the first time here, recognizing an individual who has demonstrated outstanding leadership for the benefit of our community and being transformative for the benefit of our association and the European microwave industry. So it gives me great pleasure to announce that the late Roberto Sorrentino is to be awarded posthumously the Distinguished Leadership Award for 2022, recognizing his leadership and distinguished career in microwave, millimeter wave circuit designs and antennas. Latterly, he was given the IEEE Microwave Career Award. He was a founder member of our European Microwave Association, which was created in 1998. And latterly, in 2020, he was awarded the Grand Officer of the Order of Merit of the Italian Republic. So it gives me great pleasure to invite onto the stage Linda Sorrentino to receive.
Would like to say a few words. So thank you to UMA. I'm very touched of this award. Of the many awards that my husband, Roberto Sorrentino, received during his career, I think that this is the one he would would have appreciated most. As a co-founder of the EUMA and its president for several years, I was very fond of the association and proud to be an active part of it. I'm deeply touched and grateful to EUMA for this award in appreciation of his tireless activity as a leader in research, teaching, Italian and international organizations, and in his later years, also in business. Whether my husband was a leader, there's no doubt. Was someone people felt comfortable turning to, listened to everyone, solved hard problems with unexpected solutions, and complex issues with diplomacy. He inspired and encouraged those who came into contact with him, whether they were students or colleagues. Also, he was not afraid to take on responsibilities and pursue ambitious goals, even apparently impossible ones. And definitely the most ambitious and the one he was most proud of was his company, F Microtech, that came a long way since he set it up in 2007 with a small group of his former students, and today ensures a future to over 35 young people who work there. He was a person who never got discouraged and made perseverance and self-control his most treasured attributes, always considering it a privilege to have a job he enjoyed so much. During our 27 years together, to me he was a rock, an example, and a mentor. He was definitely a leader, a guiding light that's still present for me, and I'm sure that many of you who worked with him have the same feeling. So I sincerely thank the European Microwave Association for giving the first Distinguished Leadership Award to Roberto Sorrentino. Thank you very much.
Okay, thank you very much, Linda, for those moving words. So we now move on to the relatively recently established Pioneer Award. We've had two recipients so far in 2018 and 2020. So the Pioneer Award is for those who are responsible for a noteworthy advance in the field of microwaves, which has had a lasting and significant effect on the microwave community. And it gives me great pleasure to announce that Marianne Pospieszalski is the winner of the Pioneer Award 2022. Some 33 years ago, he suggested a different approach to modeling noise parameters of FETs, and this has had a huge impact on the development of cryogenic receivers, especially for radio astronomy observatories worldwide, and this has been over successive generations. And Marianne has been recognized by a number of professional organizations recognizing this huge impact of his contribution. So I'd like to ask Marianne now to come onto the stage to receive his award.
All right. Well, you know, I have my Oscar moment here, and of course I will not cry, but hopefully I'll give you some perspective. Well, dear President Van der Bogart, dear Frank, dear Professor Gibson, dear Andy, ladies and gentlemen, dear friends, and I have had so many of you throughout my 55-year career. Certainly, let me first express my heartfelt thanks to you and to the members of the awards committee. and to the nominator and referees for this treasured distinction. It is a consequence, as Andy has mentioned, of my suggesting some 33 years ago a different approach to modeling of noise parameters of field effect transistors. For those working in radio astronomy instrumentation in the early 1980s, it was quite obvious that cryogenically cooled HEMTs or FETs will revolutionize, will open new experimental frontiers both on the ground and in space, providing we could learn how to design the cryogenic amplifiers with optimal noise performance over large RF bandwidths. The introduction of this noise model was a simple answer to that need. Soon the model has been used in the successful design of all cryogenic receivers for radio astronomy, both ground and in space, and my favorite project was, of course, cosmic microwave background experiments, including WMAP. It means Wilkinson Microwave Anisotropy Probe, and then low-frequency instrument on Planck. So the success of those efforts would not have been possible, of course, without many people that I have greatly indebted to, especially my present and past and present collaborators at NRAO, especially Dr. Weinreb, whom many of you might know, who set me up 40 years ago for the career in radio astronomy instrumentation. I'm very happy to say that I have had over the years many successful collaborations with European institutions, and there are so many: Max Planck Institute in Bonn, Onsala and Chalmers in Sweden, Jodrell Bank in Cambridge in UK, Metsä Hovi in Finland, Toruń Observatory and Warsaw Technical University, my alma mater and my home country, of Poland. I'm also very grateful to my colleagues from Fraunhofer Institute and Ferdinand Braun Institute in Germany, whose early papers on this model were instrumental in its wide adoption. It seems therefore fitting this award is bestowed by European Microwave Association, as my career spans towards European and American, and I hope I was able to contribute to that collaboration over the years. So, last but not least, I need to acknowledge the love and understanding and patience of my family, especially of my wife Maria, while at times I spent many evenings in the lab. So I'm deeply humbled for this recognition. Once again, many thanks to you all. Dear friends, it's a great honor to be here with you today. Thank you again.
Congratulations.
Thank you. Thank you.
So we now move on to another relatively new award. It's this Roberto Sorrentino Prize, again in recognition of an outstanding young professional with distinguished technical achievements within the microwave fields of interest. I'd like to thank Renato Lombardi and colleagues for organizing the awards panel for this particular prize. It's the second time we've given the prize. Earlier this year at the 2021 event, Dimitra Saikogiu was awarded the first Roberto Sorrentino Prize. But it gives me great pleasure to announce the second Roberto Sorrentino Prize for Xiaobang Shang. Well done, Xiaobang. I think Xiaobang is in shock. It's a complete surprise. Would you like to come up here and make a 10-minute speech, please? Thank you. So we now move on to the certificate of appreciation for those individuals who've given exceptional support to the microwave community. And in particular, our chair of the 24th European Microwave Week earlier this year, under very challenging circumstances, towards the end of the lockdowns, there was great uncertainty, delays, whether we're online or in person, and Nick Gridler handled that as chair of that European Microwave Week 21 exceptionally well, with calmness and professionalism. So very, really appreciate everything you did, Nick, and we had a very successful event at Excel. So well done. So please come up and start. And finally, we move on to the 2021 International Journal of Microwave and Wireless Technologies Best Paper Award. For this, I must thank Francisco Medina Mina for his leadership in organizing this award. And I'm not sure if the awardee is in the audience, but the best paper was on, title was Toward a Fully Integrated Automotive Radar System on a Chip for Philip Ritter. I don't know if Philip's in the audience or not. And so that brings us to the end of session. I'd just like to finally congratulate all the awardees again, thank everyone behind organising these awards, and just wish you a great conference. Enjoy yourselves. Thank you very much.